Hey guys, welcome to a brand new topic on electricity. And with all new topics, just gonna introduce you to my good friend. Okay, he is, yep, you're right. He's a commando, all right. And well, don't just call him commando, don't call him that. He actually has a name. His name is Coulomb, okay? AK Coulomb to be exact, okay? So I'm just gonna put Coulomb into a mission field and boom, okay, let's watch him here. Okay, so what do I have here? I've got one Coulomb here at the start of a mission field. So you can see we got a switch here, we got this stands for battery, and this is just a resistor, also known as I would call the barrel climb, okay, in our Ninja Warrior obstacle course. Okay, so if I were to close the switch in 3, 2, 1, boom, okay, oh, watch how he goes, okay, and let's see how fast he goes. Okay, well, I need a stopwatch. Someone hand me a stopwatch, please, and oh yeah, thank you. Okay, you can see my stopwatch actually recording in 1 second here, and I'm just gonna do super slow-mo here, okay? And just gonna count how many times it's gonna pass by my stopwatch in 1 second and go. Okay, one, two, three, four, five. Okay, passes by 5 times in 1 second. So what does that mean? 5 coulombs passing through in 1 second. Well, I could summarize that into 5 coulombs per second. And oh, we call this actually 5 amperes, all right, or AKA, all right, 5A. I'm sure you're familiar with this. So, what is electric current? Electric current is basically formed by moving charges. It's the rate of flow of electric charge through a given conductor, okay? And this is the formula for electric current. I equals Q over T, where the SI unit for Q is actually, yep, our brother, the coulomb, okay? So number of coulombs per unit second, that gives me current here, okay? And that is the SI unit, which is ampere. Okay, so how do we measure electric current? We measure using an ammeter to measure, and it should be connected in series, just like here, my stopwatch is connected in series to it, right? Okay, so just a little bit of history about a conventional current and electron flow. Okay, previously people always thought conventional current moved from plus to minus, so many books were written about it. But in 1897, they discovered the real truth is that electrons flow in the opposite direction. So what's gonna happen? Are they gonna change all the books? Okay, nope. Someone found a great idea. Okay, what they're gonna do, they just gonna say, all right, let's just continue using conventional current. And although electron flow is correct, is the truth, um, we just don't use that in all our conventions. So in all circuit diagrams from now, everything is using conventional current flow. Okay. All right, with this, let's move on. Okay, you remember our good friend here, Brother Coulomb, right? That's right. I'll equip him with something, give him a bag containing. Okay, what do we have here? That's right. He's got some energy bars. Okay, so what are you going to do with that? Okay, if you put him into the mission field again, this time we've got two obstacles here, right? We've got a oven and a light. Okay, so if I were to start him moving, you notice something? Okay, just a couple of coulombs here. Just throw in a couple of coulombs. In real life, many coulombs are moving. Okay, the current is actually a continuous flow. You notice two things. First, as he travels through each obstacle, you can see with 5 energy bars, oh, depletes to 2, 2, depletes to 0. Okay, he actually releases energy bars as he goes through each barrier, each resistor here. Okay, and the other thing you notice is, oh, as he just before he goes back into base station, which is known as a battery, he actually has nothing, no energy left. And as he comes out, oh, the base station, the battery gives him full bars. Okay, so this is actually what happens to the energy here. Okay, you can know, oh, it actually goes out. For the oven, it loses as heat, and for the light, it loses as light. That's it. Okay, and this is the concept of EMF, which is supplying energy to each coulomb, and potential difference, which is taking away, okay, the taking away or the emitting of energy from each coulomb. Okay, so what is EMF, also known as electromotive force here? Okay, electromotive force is defined as work done by the source in driving a unit charge, okay, 1 coulomb, okay, around one complete circuit. Basically, a number of energy bars, like what I showed you in the previous one. Okay, this is the formula E EMF, which is E equals to work done per unit charge. So it's energy bars per coulomb, right? Okay, so that is the SI unit is actually the joule per coulomb, or also known as, that's right, I'm sure you've seen this before. Okay, that is the basis of 1 volt. Okay, and potential difference is similar, except that it is the energy to drive a unit charge through one component here. Okay, so SI unit, also known as the volt. Okay, so in short, okay, if I were to just compare EMF and potential difference, EMF is to drive a unit charge around whole circuit, whereas potential difference to drive the unit charge just through the component. That's it. Okay. So how do we measure EMF and PD? As opposed to current, we measure it using a voltmeter, and they are connected in parallel. Why in parallel? Because I need to know how much energy actually gets consumed by the resistance. I need to put a one wire before and one wire after, so that I can measure the difference. That's why the second word in PD, potential difference, is actually, you guessed it, it's difference. So potential difference, just the difference in potential before and after. Okay, so that's why I need to connect it in parallel. All right. So in short, this is what we've learned in today's video. Okay, current, EMF, potential difference. The symbol current is I, EMF E, potential difference V. Okay, current is just simply how fast the charges move, and the SI unit is A, the ampere, whereas EMF and potential difference is the volt, known as the V. Okay, and I measure using an ammeter in series for current, and using a voltmeter to measure EMF and potential difference in parallel. All right, so just to do a quick recap, okay, remember, we started off with a brother Coulomb here, who is actually a charge. Okay, the symbol that we use is actually Q. Okay, so how fast does Coulomb move? Okay, is just the current. So current equals to Q over T. That means how fast the charges actually move. Okay, but how much energy does each charge possess? There are two things. Okay, it's either the EMF or potential difference. The similarity between both of them, they both have the same SI units, which is the volt, but the main difference is that for EMF, it is supplied by the source, whereas for potential difference, it is to drive energy through the component itself. Okay, so this one is supplying of energy, this is consuming of energy per unit charge. Okay, with that, I hope you enjoyed this video. I'll see you guys in the next.